Hi everyone. Now we come to the fourth lecture already in the module 4 about electric field and magnetic field. We have all finished the things about electric force, electric field, and electric potential. And the last two lectures will be about magnetic. So today we are going to talk about magnetic force in the first part and the source of magnetic field in the second part. For the first part, magnetic force that is caused by the magnetic field, what we see from this one, what we see from this slide is, let's say, it is the Earth and is magnetic. The Earth magnetic is causing the interactions and causing the force to the particle from the sun, so that it protects the Earth from the particles from the sun. Okay, but there is going to be some particles from the sun that can come to the North Pole and to the South Pole through the magnetic field of the Earth, and this leads to the famous phenomena of the aurora. Okay, and what we see from the motion, from the helical motion, little helical motion of the charged particle over here. Yeah, that you can see that the particle travel along the helical path through the North Pole and through the South Pole in this fashion. This is caused by the magnetic field. Okay, so magnetic field will affect the particle with charge and with velocity, and this is what we are going to discuss in this handout. And the same principle, okay, is applied when we try to put the current in the loop. So there is going to be the current in this direction and the current in this direction. So if you think about current as a number of charges moving within the conductive wire. So on one side, the charge moving in a wire will cause a force, and in the other way, the charge moving in the other line will cause another force, and two coupling force will generate the torque that can rotate the wire. So, and that is the principle of electric motor. Okay, so the outline of this first part, we discuss briefly about magnetic field, magnetic force on moving charge, circular motion, helical motion, and the charge moving under electric field and magnetic field at the same time. Then magnetic force on the current carrying wire and the magnetic torque. Okay, magnetic field. What we know about magnetic field? So we originally know that magnetic field come from magnet with North Pole and South Pole. So the Earth itself is also a magnet. So we know that the Earth, the North Pole of Earth, is actually having the South Pole magnet, and the South Pole of Earth is having the North Pole of magnet, and the magnetic field is defined its direction by coming out from the North Pole and going into the South Pole. So that's we always see that magnetic field of the Earth is in the direction towards the north. Okay, that is why if I put the compass here, the pin in the compass will always pointing to the north. Okay, and then we can also generate a uniform magnetic field somehow if we design the shape of the magnet to be in this fashion. Okay, to be like a plane. So just like what we did to generate electric field. So if I have positive charge and negative charge in the pair of plates, it can generate uniform or constant electric field. But in this case, we have the North Pole and the South Pole aligned in a couple of plates. okay, and it would also generate the constant or uniform magnetic field, okay. And in the first part, we are focusing on the phenomena that happens under the uniform magnetic field, okay. We are considering the charge moving into uniform magnetic field. We are considering the current in a wire and within a uniform magnetic field. Okay, so we're discussing about the notation that we are going to use along this slide. Okay, so magnetic field. Okay, we are going to say that it is the vector quantity. Okay, so when we say there is a vector, it should have direction. Okay, so the direction of the magnetic field. So if magnetic field go to the right, go in the up direction, go to the left, go into down direction, we represent magnetic field like this. Okay, but sometimes if I want to mention magnetic field in the direction that is out from the screen, okay, so just pointing towards you guys from the screen, okay, we use the dot to define that direction. But if you are talking about magnetic field that is pointing into the screen, or magnetic field that pointing towards me when you are looking at me, you use the cross instead. Okay, so you try. Okay, so it's just like you try to think about the arrow. Okay, yeah. So if the arrow like pointing out, you're gonna see like this side of the arrow, and if the arrow pointing into the screen, you are going to see this side of the arrow. Okay, so magnetic force on a moving charged particles. Okay, so okay, so this is a good animation. This is a good animation that tells you about the direction of the magnetic field. We use right hand rule to describe it. Okay, so first, sorry. Okay, so firstly, we consider a particle of charge q. Okay, like here, this is a particle with charge and move with velocity v within a magnetic field b. So this one, you can see that the direction of the magnetic field b is going into the screen. Okay, pointing into the screen, and we can show that the force that is acting on the particle is q v cross b. So the sign here, it is, we call this the cross product. Okay, cross product of the two vectors. Okay, so that's the vector f, or force, is the cross product of velocity and magnetic field, and times by a constant q. Okay, and how to find the direction of the force? Okay, you use the right hand rule. Okay, so here you can see that we. Okay, so let you see the animation again. So v is in this direction to the right hand side. Okay, start from the right hand side, and b is the direction in green. Okay, so and that is how you are going to define the f, or the direction of the force. Okay, so it's just like you pointing your fingers in the direction of this velocity. So if your charge is moving in this direction, you point your four fingers there, and then the direction of the magnetic field will be perpendicular to your palm. This pen is a magnetic field, and then you close your hand, and then your thumb, the direction of your thumb will be the force. Okay, so doing it this way, we are going to determine the direction of the force. Okay, for example, in the picture here, okay, I try to demonstrate. So we can see that the particle is moving to the your right hand side. Okay, it is your right hand side. Then the magnetic field is moving. The magnetic field is moving toward the screen. Okay, so maybe it's better to draw the picture here of your right hand. This is your four fingers. Okay, and then you turn your forehand. Okay, you turn your forehand into the direction of magnetic field. And if you use your right hand, you're gonna find that your thumb is up. Okay, so when your thumb is up, the direction of your thumb is the force. So we get the force in the up direction for the positive charge. But for the negative charge, okay, negative charge, things will be opposite because we get the minus sign in front of the Q. When we get the minus sign in front of the Q and we get the minus sign in front of the force F, the direction of force F become opposite. Okay, so that's in this picture. We're gonna see that the velocity, if the negative charge moving to the right hand side, okay, it will have the force that coming down opposite to the positive charge. Okay, and then for the case that there is an angle theta between V and B, okay, because in this case, in some case, if velocity and magnetic field is moving in the right angle, so if theta is 90 degree, in this case, okay, like if the vector B is pointing in and vector B is going to the right, here I can say that theta is 90 degree, is making the right angle. So when making the right angle, sine theta will become 1. When sine theta will become 1, the magnitude of the force will become just QVB. Okay, so this is what we get in this case on the left hand side. But if theta is not 90 degree, we need to use this formula. And then when we consider the case that theta is 0 degree, for example, particle moving in this direction and in parallel to magnetic field, or particle moving in the opposite direction as a magnetic field, we are going to get no force. And for these cases, okay. So that's just please remember, okay, this formula, QV cross B. So V come before B, okay. So V come before. So when you use the right hand rule, you use your fingers for B. Use your forehand, okay, forehand as B. So V B, and then thumbs up, and then you get the F in the direction of your thumb. Okay, so here we give you some other case studies. So in the case that V, or the direction of the motion, okay, so velocity, so it move up, and the magnetic field is on the right hand side and is making the angle of 90 degree. Okay, so in this case, theta is 90 degree, and F will be QVB because sine theta is equal to 1. Okay, you're gonna get the maximum force on the particle. Okay, but if particle moving in the same direction as the magnetic field, you get 0. Okay, because psi 0 is equal to 0. Okay, and you get no force. You get no force when particle moving the same direction. But if it makes some angle, okay, so the force will become QVB sine theta. Okay, magnetic force, circular motion in a uniform field. Okay, from the equation of the magnetic force. Okay, in case that theta is 90 degree, you can see, so if the field is uniform and the angle is 90 degree, what we will observe is the circular motion. Okay, and for this circular motion, the magnetic force. Okay, so the magnetic force will become the centripetal force, or this magnetic force from QVB will have the direction that point to the center always. Okay, so because when you consider this point, okay, and try to use the right hand rule like this, you always have the force pointing up. Okay, but when you consider this point, like this point, when your particle is moving up, okay, using the right hand rule, you always have you're gonna have the force pointing to the center, and then in other case, if the particle moving down, okay, and on the other side, um, using right hand rule, you have force to the left and to the center, like this. Okay, so this case happening in under the uniform magnetic field, that you always have force pointing to the center, and then we match the force to the center, or centripetal force, with the force from magnetic field, or QVB. Okay, so that will lead to the relation. Okay, okay. So this one is this slide is trying to get you the ideas of the directions. Okay, and okay. So let's try to answer this question together. If we have a part like this, so it starts from down and curving and going up, curving and go to the left hand side. This one should be positive or negative. Okay, so I would consider 1 point. Okay, so if it move in this direction, and I have the vector v for the velocity, and and then I know that the force F is acting toward the center. Okay, and then I'll try to check with QV cross B. So if B, if I use the right hand, and then pointing my palm towards the screen, I'm gonna see that V, or my four fingers. Okay, V, or my four fingers in this direction, and my thumb in this direction. Okay, and then my palm, okay, is going into the screen. Okay, so that we can see that this is according to the right hand rule. Okay, F, V, and B is following the right hand rule. So if it follows the right hand rule, okay, so we can say that the shot is positive. But if it happens to do the opposite, such as if you have electron, and electron is moving in this direction with V, okay, and I try to put my right hand, okay, to put my right hand face down to the screen, okay, and then here I actually have the thumb up, okay, the thumb up for positive charge, but for negative charge, okay, we have the force going down. Okay, we have the force going down because Q is minus E, because we have the minus sign, we have the opposite charge, and hence we have the opposite force. Okay, so we come back with the relation centripetal force is equal to magnetic force. So we try to match FC with FB. So we have, and FB is QVB. Okay, we neglect the sine theta, because if theta is 90 degrees, sine theta is equal to 1. And then we try to derive this formula. So from the formula of centripetal force, we have AC as V square over R for any circular motion. Then we come up with this relation. We can calculate the radius of circular motion. So radius of circular motion will depend on the magnetic field and will depend on the speed of the electron or of any charged particle within the uniform magnetic field. Okay, so this is what we actually observe. Okay, in when we actually try to accelerate the electron in the magnetic field. Okay, so from this apparatus, okay, this coil, okay, so can generate the magnetic field that passing through the coil like this. Okay, so from this picture, magnetic field is passing through the coil. Okay, and then when we try to eject the electron, okay, the electron beam is in blue. Okay, electron will travel in one direction. Okay, let me change. Okay, let me change to light blue. Okay, we tend to move in one direction that is perpendicular or making the right angle or 90 degree with the magnetic field, and then there will be force FB that acts on the electron then and make it curve. It will be curving about the magnetic field and making a circular motion. Okay, but as you can see, okay, if you eject the electron in the direction that is 90 degree with the magnetic field, you have the force that is pointing toward the center. But if the electron has been shot in the direction that is not 90 degree, what we're going to have is we're going to have the helical path, because the velocity of the electrons can be divided into the component that is making 90 degree and the component that is making that is parallel to the magnetic field, and there's no magnetic force. Okay, so here is some sample calculation. Okay. Change the pen color a little, back to red. Okay. Okay, so electron beam with the speed. Okay, so we have the V here circulating with radius. So we got R, and they asked you for the magnetic field. So we can easily get the relationship that you got from the FC equals FB, and FC is mv squared over R, and FB is QVB. So that's so that you can get this relation, and you can use this relation with the given R, with the given B, and when you say electron, you know the mass of electron. Okay, and with the Q, you know the charge of electron. Okay, so finally, you'll be able to find the B or an unknown values by substituting the mass of electron and the charge of electron, and substituting the radius of the motion R, and substituting the speed V, and should be able to get magnetic field. And then another example, okay, in which we are working in the much more details in the example class. Electron accelerated from rest by the voltage 350, okay, that should be the unit volt, into a uniform magnetic field. So they already give you the B, and perpendicular to the motion. So when we say perpendicular, that means theta equals 90 degree, And when theta is 90 degree, FB is equals to QVB for sure. And find the speed of electron and the radius of circular motion. So we divide the discussion into two parts, okay? Because electrons were accelerated from rest by the voltage, okay? So let's try to recall this equation from the lecture 3. Okay, from lecture 3, we use the electric potential energy, or U, and U, or potential energy, will be changed into kinetic energy of the particle, or of the electrons. Then we can then find the speed, because we know the charge of electron, we know the mass of the electron, and we are given the volt, so we are able to find the speed. Then when we already get the speed, we know mass, we know the charge of electrons, and you are given the magnetic field B, then you'll be able to find the radius R. Okay, so finally, with given voltage V, okay, and magnetic field B, you can find the radius of the particle's motion under the magnetic field. So magnetic force and magnetic field. Okay, so in this case, we are going to consider the system that you have both electric field and magnetic field at the same time. Okay, you have both magnetic field and electric field. So with electric field coming down, okay, with electric field coming down, you are having the Fe, or electric force, coming down in case that your charge is a positive charge. Okay, when positive charge, the magnetic force, or Fe, okay, so with electric field E, the force Fe will be the same direction. Okay, then when positive charge is moving with the velocity v within the magnetic field that is going in, okay, using right hand rule. Okay, so if I put my hand like face down, okay, so face down to the screen, so face down to the screen, my 4 fingers are here, then my hand face down mean magnetic field in, then I get the force F going up by the direction of the thumb. So that's I get the FB that is going up. So with FB going up, FE going down. If FB equals FE in magnitude, okay. So with FB and FE equals in magnitude, we can cancel these two forces. So when we cancel these two forces, okay, so we can see that the particle can move in the straight line. Okay, so that it is our work to find the condition. Okay, to find magnetic field, to find electric field, or to find anything to make the particle able to move in a straight line. Okay, then another applications, okay, is of the magnetic field and the moving charge is the mass spectrometer. Okay, so let's recall that the radius of the circular motion, okay, is R equals mv cross qb. Okay, so that you can see that the radius of the radius of the motion will depends on mass and will depend on the charge. Okay, so that's if you want to try to separate, okay, to distinguish, to make difference between different kind of particle, because if you try to shoot electron, if you try to shoot nucleus of helium, if you try to shoot nucleus of hydrogen, if you try to shoot nucleus of lithium, okay, they have different amount of mass and charge, okay, and that will give you different radius, okay. Then you can tell you can tell from looking at the path, okay, which one is helium, like you can say like which one is proton, which one is lithium from using this mass spectrometer. And and also from this from the principle from the last slide, you can control you can control the particle to move in a straight line with this relation, with V equals E over B. Okay, then for the helical motion, okay, this is the case that we try to we try we try to shoot the particle and making the angle with the magnetic field. Okay, so that's we get the same relationship with the case that particle is moving in the perpendicular direction. So that's, we just need to find the component of the velocity in the in the in the perpendicular direction. So we change from v to v sine theta instead in order to calculate the radius of the helix. Okay, so the example of the helical motion of the charged particle was the aurora. Okay, so the aurora come from the particles that come with the solar wind. So the solar wind occur from the solar flare. It is the fluctuation of the charged particle within the surface of the sun. And then when the fluctuation of the solar flare or the solar storm occurs, and the charged particle or the solar wind will come with the solar wind. Okay, so this is like the electron moving along with the solar wind, and then when they face the Earth magnetic field, they get deflected by the QV cross B. Okay, we get magnetic field and we have the force F by QV cross B because the particle from solar wind has some charge. Okay, but then there will be some charges that is not deflected outside, but they travel along the magnetic field in a helical path like this, in the same helical path like this, and then when they collide with some atoms on the when in the Earth atmosphere, they will excite those atoms, and when atoms are excited and they move their energy level back to the ground, they will emit some light, and this is what you see as the aurora. Okay, so we are looking at some more examples from in the case of charge moving under magnetic field. So we say that particle of charge Q and mass m perform circular motion in uniform magnetic field, and then they ask us to find the period. Okay, so how to do this? Let's recall this R equals mv over qb, the radius of the circular motion under magnetic field again, and then we can define the period by the time of a complete cycle. Okay, so if I start with, okay, so here if I start with v is distance by the unit of time. Okay, and we consider a full turn. Okay, one period of a full circle of motion. Okay, the distance will be like 2 pi r. Okay, and the time will be t, or this is the motion of like one period. Okay, so that's from this relation, I can say that t or period is 2 pi r over v, and then from r as mv over qb. Okay, we can derive the new formula for the period. Okay, so that's how we do it. Easy. Then particle undergoes a uniform circular motion. Okay, and we are given the radius of the motion. We are given the magnetic force. Now, here we are already given the magnetic force, and they ask us for the kinetic energy. Okay, so you can start with the circular motion of the force. Okay, but so this one, I think that this is not necessary to be the case of magnetic fields, but any kind of circular motion. If you know the force that is acting toward the center, we we say that centripetal force is mv squared over r, and when we have the mv squared over r, I put half, and I put 2 times 1 over 2, and then mv squared is still here, and then 1 over r is still here, and this is the kinetic energy. So that now you can then write down the kinetic energy in terms of F and R, which is half Fr, and you can use F and R from the question to calculate for the kinetic energy. Okay, and then now it is the case that we consider the electron that move within both magnetic and electric field. Okay, so in this case, we are showing that the first part, we need to calculate the kinetic energy. Sorry. The first part, we need to calculate the kinetic energy and the speed from accelerating the electron. Okay, so this is the first part. We use some kind of voltage to accelerate the electron. Okay, so that we get the EV, or the potential energy, and then half mv squared as a speed. Then we're gonna have the terminal speed v. Okay, that is of the electron that will come to the magnetic field, and then using this condition. So this condition, we get this from Fe equals Fb. Okay, in order to make a electron travel in a straight line, we need to control Fe equals to Fb. Okay, when Fe equal to Fb, Fe, or electric force, okay, is a product between a charge and electric field, and Fb, or magnetic force, whenever the particle moving in the perpendicular direction, it is a QVB. Okay, so from this we can derive V equals E over B. Okay, then from this we use the speed that we get from the first part. Then after that we derive for the ratio between E and M, and then from here we can calculate the ratio between charge per mass of an electron by measuring electric field, measuring magnetic field, and measuring the accelerating voltage. Okay, so the next example is about the mass spectrometer, as we discussed before. Okay, so they say that two isotopes of helium nuclei, okay, He3 and He4. Okay, so here we need some general knowledge in chemistry, a little. Okay, so we need to know that for helium nuclei, okay, the charges of these two isotopes should be plus 2e, both plus 2e. Okay, so for helium-4, we have like 2 protons and 1 neutron that make 3 nuclei in the nucleus. And for helium-4, we have 2 protons and 2 neutrons. Okay, so helium-3, we have the mass, we have the charge of 2 and the mass of 3u, but for helium-4, we have the charge of 2e and the mass of 4u. Okay, so they are accelerated through the same potential difference. Okay, so that's using the potential difference. Both of the particles will have EK, or we have the kinetic energy of EV, sorry, of QV. Sorry. Okay, and for the kinetic energy, it would be the half mv square, and it would be, and this would be 2ev. So that's the velocity. It would be 4ev over m and the square root. So that's they have the speed of 4ev over m, but for m would be equals to 3u for helium-3, and would be equal to 4u for helium-4. So that's the velocity will come out a little bit different there. Okay, so as a result, okay, so we have that v square is 2qv over m, and then if and then if we try to write down this relation to compare the speed of helium-3 with helium-4, because we see that v square and m is inverse proportional. Okay, so v square is inverse proportional to m. So that's when I write down the v square of 3, the mass 3 will be here, and when I write down the v square of helium-4, the mass of m4 would be here. Okay, so that's so that we have this relationship, and we keep this relationship to calculate the things about radius. And then from the radius, r equals mv cross b. Okay, so we have that r is proportional to m and v, because q we have the same charge. B we are accelerating through the same potential, so r is proportional to m and v. So when we have r proportional to m and v, so r3 will be on the same side as m3 and v3, and r4 is with m4 and v4. Then we use the relationship between v3 and v4 from the left hand side, and so that we come out with the last relationship between the radius of helium-3 and radius of helium-4. So that is the difference in the radius that we can observe between these two isotopes. And this is the use of mass spectrometer to differentiate or to separate these two isotopes from each other through the different radius of the motion. Okay, so that's if we say that R3 and R4 has the ratio of 0.87. We can see the part of helium-3 like this, and we can see the part of helium-4 here. Okay, so magnetic force on the current carrying object. Okay, so we sort of try to think that the current is a moving charge. So when we got the current, when we got the charge moving, there are magnetic forces acting on the charges. So that when we have the current, magnetic force will act on the wire as well. So so now, if I consider the current moving in the upward direction, and here we have the magnetic field that's coming outside. So now we use the we use our right hand face up in this way. So when I use the right hand face up, I can see that this is my right finger, and this is like my forehand. This is my whole forehand because the magnetic field is coming outside. And then we have the thumb pointing to the left hand side. So that is the force that is acting on this wire and makes this wire to distort in this direction. Okay, but if the current coming down, okay, using the right hand rule again. Okay, so this is just like uh, the upside down motion of the last one. Okay, so if I get the forehand of my right hand out, and then the four fingers pointing in the same direction as the current, I'm going to have the direction of the force to the left hand side. Okay, so that comes to this equation. Okay, F equals IL cross B. So it is essentially similar to what we have to QE cross B, because if I say that the charge, sorry, the current is actually dq by dt, or the rate of change of the electric charge. Okay, so here I can say that I here is dq by dt, and times by L, and cross by B, and cross B. Okay, but if I look at I treat the charge as a constant, and I move the d by dt differential operator towards the L, dl by dt will give us the velocity v. So that is, they are actually like the same relation. Okay, but this one, we are writing this in terms of the current. Okay, and the same, if current, okay, if current that is in the same direction as the vector L is making the angle theta with the magnetic field, the magnitude of the force become ILB sine theta. Okay, and there are some cases to consider. Okay, so if I and B making the angle theta, if I and B making angle theta, the magnitude of force will be ILB sine theta. And when if I and B are making the right angle, okay, so the magnitude of the force will be ILB. Okay, and this is another case. If I and B in the same direction, theta equal to 0, we have sine theta equal to 0, and we have no force acting on the wire. Okay, and for this case, if I is pointing into paper, yeah, like this case, we still consider the angle as perpendicular, so that we have the force acting with the magnitude ILB. Okay, and according to the right hand rule, I think that the force should be towards the right hand side. Okay, so this is the example case. So here you have the current moving in this direction, and then it is within the magnetic field that coming down, okay, coming in downward direction from from North Pole to the South Pole. So with magnetic field that come into the downward direction, okay, you use the right hand rule, and then pushing your finger in the same direction as the current, then you can see that there's a force dragging the current bar into the left hand side. Okay, so Yeah, here we give some simple example of the charge from the current of 10 ampere, making angle 30 degree with the magnetic field, and we straightforwardly give you the magnetic field strength. Okay, so we can use the formula ILB sine theta in order to find the force acting on this object. Okay, and then with an applications and with the mechanical equilibrium, so they they try to ask you for for the condition in which tension in the supporting wire to be 0. So if the tension in the wire is 0, we need to say that FB is equal to mg, or the magnetic force and the gravity are in the equilibrium. And magnetic force, we can use formula ILB, and then we need to find the I and using the information from the question. Okay, and then magnetic torque. Magnetic torque occur when we have magnetic field, and then we try to give the current into the coil. So if I give the current in this direction, in the clockwise direction, the current on the left hand side will go in this way. The current in the right hand side will go in this way, and then according to the right hand rule, it will generate a magnetic force in the upper direction on the left, and lower direction on the right, and the couple force will rotate the coil in this direction, and then we have the formula to find the torque. Okay, using magnetic force F and times by the width of the coil, and that will give you the magnetic torque of IBA. So if if you have the coil of having many turns, the I, or the current, will become N, or number of turns, times by I, so that the torque will be given by NIBA. And which is like the principle of the motor, electrical motor. Okay, so that again, so if we continuing like giving the current to the conducting coil, that will be forces in green, in the green arrow. Okay, to the opposite. So the force on the opposite direction of the coil will be also in opposite direction, and that will create the torque on the coil. Okay, so that was the end of the first part. So we come to the second part about magnetic field and Ampere's law. So as we can see from the first part, okay, from many parts, we see that firstly we have the magnetic field. Just a second. Firstly, we have magnetic field, and we have the current flowing in the magnetic field, and and then it will generate the force. And also, if we go back to the it will go back. Okay, that sorry about that. Oh, sorry about that. Okay. Okay, so if we go back to the part of charge moving in magnetic field, we already have the magnetic field, and then the magnetic field will generate force on the moving charge, or it would generate force on the current. Okay, sorry, just a second. Okay, so but in the second part about magnetic field and Ampere's law, we're trying to think the other way around. We're trying to think that we start with having a current, and the current can give you magnetic field. Okay, so let's speak clearly again. Okay, so in the first part, we consider magnetic field that we already have magnetic field, and it can generate force on the current or on the moving charge. But on this part, the current itself can create magnetic field. Okay, so let's see how it goes. So what do we see here in the applications? Okay, firstly, if you look at this system, okay, so we try to give the current to the wire, okay, and then try to look at this, try to look at the compass, okay, direction of the compass. So with the compass, what we always see from the compass is it should always pointing up the north, to the north direction, because the magnetic field of the Earth, I said that this is a B Earth. It is in the northern. It is pointing towards the North Pole. Okay, but for this case, if I give the current, I to this wire. Okay, this current will make the compass go wrong. Okay, it made the compass go wrong because the current generates another magnetic field. Okay, it would generate magnetic field that is stronger than the Earth magnetic field, and you can see that the direction of magnetic field is making a circular path, and it make the compass to turn in the same direction as the magnetic field. So that we have a picture that if I get the current can create magnetic field around the current line. Okay. And then what is happening with this two wire? Okay, I give the current in the first wire, and then the second wire. Okay, and then what is happening? Okay, is the wire tends to have the force, okay, that push each others out. Okay, so what is happening here? Okay, what happening is if I consider this wire as a wire number 1 and this wire as a wire number 2, and the first wire they have current flowing through it, and using the same logic as the first picture, the current in the first wire will create the magnetic field. Okay, and I say that this is a B1. The magnetic field B1 will create magnetic force on the wire 2. Okay, because in the wire 2 there is also a current, and then when the wire with a current is within magnetic field, there is magnetic force. Okay, and in the other way around, the force, the current in the wire 2 is also generating a magnetic field around the wire 2, and when the wire 1 is within the magnetic field B2 from wire 2, there is also a force acting on the wire 1. So it looks like they have force acting on each other, but that is not direct force. That is the force from the magnetic field from each others. And for this one, we call this the solenoid. And then from this solenoid, many phenomena occurs, because if I bring the current into, if I input the current into this coil, it will generate the magnetic field within the coil. Okay, and the magnetic field in the coil is very strong, but magnetic field outside the coil is 0. So this phenomena is pretty interesting, and we are going to discuss about this. Okay, so we talk about source of magnetic field and magnetic field direction, and then we are going to use Ampere's law to find the magnetic field in some cases. Okay, so magnetic field. So in the theory, okay, magnetic field occurs from moving charge and electric current. Okay, so as long as we have the charge moving, it will generate it would be a weak magnetic field, but it does generate some magnetic field around it. Okay, as we discussed before in the compass picture. And let's say that magnetic field lines will loop about the current. Okay, and the current is the source of magnetic field. Okay, so we have like many kinds of the magnetic field source. Okay, we have the solenoid for the solenoid. Okay, so apart from the current line, okay, that the current move in this direction, the current flow in this direction, and it would generate magnetic field in the direction that is determined by the right hand rule. If you use the right hand and use your thumb as the direction of current, you find that the direction of the magnetic field will be the same as your forefingers. Okay, but then surprisingly, when you consider the different shape of current, okay, if the current, okay, is not in straight line, but if current flow as a solenoid like this, the direction of the magnetic field, okay, you can also use the right hand rule. Okay, I then use my forefingers as a current, and I use my thumb as the magnetic field. Okay, so if I use the right hand rule, I get this as a current, and then I have my thumb. Direction as a magnetic field. Okay. Okay, so this is the picture that I'm going to show you, like the current loop. So using the right hand rule again, and this demonstrates how to use the right hand rule to determine the direction of the current loop. So if you see that if you use your thumb, okay, to point in the same direction as the current, you're gonna always see that the magnetic field in green will follow the direction of your rest of the fingers. Okay, so I'll let you watch this for a while. Okay, so that you can see that from here, if we try to point the thumb into the paper, you can see that your finger will be like in the clockwise direction. But if you try to pull your thumb out from the screen, you can see that your finger will be in the counterclockwise direction. Okay, and then Ampere's law. So this is the law that is used to find the magnetic field from the source. Okay, in some simple cases. Okay, so Ampere's law says that the integration of magnetic field along the closed curve equals to constant times the current enclosed by the curve. Okay, then let's have a look at the equation. So this is the Ampere's law. So this is what we say as the integration of the magnetic field along the line. Okay, and L is the length. Okay, so for this simple case of the long straight line, I try to view that integrate BDL. If we treat B, if we use the condition that B is a constant, integrate BDL can be written in terms of B times 2 pi r, or B times by the length of the path. and is equal to mu0 and times by I, okay, and in which I is the I that is enclosed by the M-pairs loop. Okay, so this loop we call this the M-parent loop. Okay, so let's have a look at this case again. Okay, so we construct the circular M-parent loop, of radius r, because we want to find the magnetic field at distance r. So this is the M-parent loop. Okay, and then we integrate BDL along the M-parent loop, and the integration become easy because we know that due to the symmetry of the system, B here, the magnitude of B here, and here and there are equal. So integrate become B times 2 pi r. Then we come up with this relation. Okay, so that we know that for magnetic field, the magnetic field strength is inverse proportional to r. So magnetic field become weaker with longer distance. Okay, and the magnetic field in a wire. Okay, so here this is the magnetic field in a wire that we calculate, and it will generate the magnetic field about it. Okay, and this is what we see in the like when we look at the compass, we see that the direction of the compass has changed from the north. Okay, and here also when we pull, when we don't give the current, you see that the compass will pointing to the north direction, but when we give the current and there's magnetic field around the wire, we see the change. Okay, and then in the same case, we try to calculate the angle in which the compass will twist. Okay, and okay, we talk about this in detail in example class again. But what we did here was we try to find the one magnetic field by Ampere's law. Okay, one magnetic field by Ampere's law. So this is a B wire. So this is the B wire, and then we have the distance r from the wire to the compass, and this is where we want to find the magnetic field. And then we combine the magnetic field from the wire with the magnetic field from the Earth. Okay, and then considering the vector addition and the right triangle, we can calculate the twisting angle that magnetic field wire, that magnetic field from the wire is making. Okay, and for the solenoid case, we can use, okay, we have a look at the magnetic field from the solenoid first. So then you can see that the solenoid can create the magnetic field that you see that the number of field lines within the coil is much more than the intensity of the field lines outside the coil. So in this case, we always approximate that the magnetic field outside is about 0. Okay, why? And when the magnetic field inside the solenoid is very strong compared to the outside. Okay, so with that assumption, okay, we try to use Ampere's law again to find the magnetic field within the solenoid. Okay, so here we create a rectangle Ampere loop. Okay, with this rectangle, you see, with this rectangle, there is only path AB. There's only part AB that have magnetic field. Okay, because we assume that magnetic field outside is 0, so we integrate only for the part AB, and then with constant magnetic field along solenoid, we can transform the integrate into B times L, in which L is the length of this ampere loop. Okay, and then with N is the number of turns that the ampere loop is enclosing. Okay, so that's for I enclosed. It's not only I that is the current. So with N turns, the current should become N times I. Okay, because this is like one. We also have current here 1, 2, 3, 4, 5, 6, 7, 8. So we need to count all the currents that ampere loop is enclosing. Okay, so that's I ENC, I enclosed become NI. Okay, and that we have this relationship. So we have B equals mu 0 NI over L, when N is the number of turns and L is the length of the solenoid. Okay, so here it comes to this example that we try to calculate magnetic field inside the solenoid, and use the relation that we have from the Ampere's law. Okay, so they give us the number of turns, they give us the current, and they give us the radius, and they give us the length. So we are not going to use the radius. We are using only the length. Okay, so that's there's the L equals 0.95 meter, and then we calculate, and then we substitute everything. We substitute the I of 3.6 ampere. We substitute N of 1,200 tons, and then we use the constant mu 0 as 4 mu. Okay, the constant mu 0 is the permeability. Is the permeability of the magnetic field within the vacuum. Okay, so using this constant, we can calculate the magnetic field. Okay, and for the toroid, just like a solenoid with a donut shape. Okay, so for the toroid, instead of L in solenoid, we replace L with 2 pi r, in which r is the radius of the toroid, and then we can also, using Ampere's law, so times B by the length, and make this equals to mu 0 Ni. And this mu 0 is a constant, is 4 pi times 10 to the minus 7. Okay, and then for another example case about magnetic field, inside and outside are cylindrical wire. Okay, so if we consider a thick wire, and here we try to calculate the magnetic field outside. Okay, so that's we are going to consider the term I enclosed over here. The term I enclosed over here will be I, because the ampere loop is covering the whole current I. Okay, so that we have the same relation as we did for the case of a long wire. Okay, so because from the Ampere's law, we times B by the total distance of along the ampere loop, B times the 2 pi r, and we have the B equals mu I over 2 pi r. But when we try to calculate the magnetic field inside, okay, if I consider just only this region, this enclosed region, okay, here the current I enclosed will not equal to I, will be less than I. Okay, so that's we need to bring the small area of pi r squared and the large area of big r squared pi. Okay, and then we use the ratio between small area and divided by the large area, and then we times this by the large current. Okay, so that's we should have the enclosed current or the small current within this circle. Okay, so that's from that relation we use Ampere's law again. We times B by the path length, and then we are going to have so if these r cancel with r squared, we have that b is proportional to r inside. Okay, so if I divide the region to be inside and outside, the magnetic field within the wire, okay, is proportional to r, and for the magnetic field outside the wire is inverse proportional to r. Okay, then for the last case, it is the case about forces between parallel current carrying wire. Okay, so as I mentioned in the picture before, okay, so so the phenomena that we can observe, okay, like, okay, so let me go back to the first page of this. Okay, so we can see that if I give the current, okay, in the of two wire in red in the opposite direction like this, okay, because the current flow this direction, come to this direction, and then come to this direction. So considering just only red wires, they have the opposite current. With the opposite current, they tends to repel each other by some forces. Okay, but if you give the current of two wires in the same direction, okay, they tend to have the force that attract the two wires together. Okay, so this is the effect of the magnetic field. Okay, so let's go back to the page. Then let's go back to this page. Okay, so giving the current I1 and I2, we have the forces F1 and F2 that that attract the two wires. Okay, but if I1 and I2 are with the opposite direction, we have the force that tends to repel. Okay, this happens because, okay, if we consider the I1, okay, will create the magnetic field B1. Okay, and then with magnetic field B1, okay, with magnetic field B1, from Ampere's law, we have mu 0 I1 over 2 pi d, right? With that, as the wire 2 have the current I2 and have the length L, okay, and have the length L, and if I2 is in a magnetic field from I1, okay, there will be force F2 that is equals to I2L and magnetic field B1. But the other way around, I2 will also generate magnetic field B2, and B2 can be calculated from Ampere's law. So it's mu I2 over 2 pi d. And this B2 will have some effect on I1 because the current I1 within the wire of length L is within the magnetic field B2. So there will also be the force acting on the wire one. Okay, so yeah, so this one, yeah, they try to do experiments. One giving currents in same direction, then opposite direction. Okay, and same direction they will attract, then in opposite direction they will repel. Okay, and then yeah, we can calculate the force by firstly calculate magnetic field from wire 2, and then the force, and then wire 1 will experience the force from ILB2. Okay, because B2 is B2 is generated from wire 2, and then wire 1 is sitting within the magnetic field of wire 2. Then we substitute the B2 into this equation. Will give us the expression of F1. Okay, and we can write down F1 in terms of I1 and I2 and the distance d, and also the magnitude will be equals to F2 because the Newton's third law, but the direction will be opposite. Okay, so that if F1 is in this direction, F2 will have the same magnitude as F1, but with opposite direction. Okay. All right. So this is an example of this is not a wire with wire, but it is a wire with charge. Okay. So they say that a proton is moving at a velocity v towards a straight wire, and the proton distance from the wire is d. And what is the magnetic field? Sorry, what is the magnetic force on the proton due to the current? Okay, so we say that the current is now actually creating a magnetic field. The current creating magnetic field in this direction. Okay, so viewing from the downward direction. Okay, so we see that the current here at this position is going into the paper, right? Using the right hand rule. Using the right hand rule. So this thumb is the current, and the other fingers are magnetic field. And at this position, the magnetic field will be coming into the page, the screen. But considering at the upward position, okay, or at the plus y direction, the magnetic field will have the direction come out from the page. Okay, so with direction that come out from the page, and then we try to see magnetic force acting on the charge. Okay, so we are going to do the QV cross B again. So cross product between V and B again, using the right hand and face up. The right hand face up. So face up because of the magnetic field coming outside. Okay, so the right hand face up will give me something like this. Okay, that's that the velocity coming into the downward direction, and then the face up hand, okay, will give direction of the magnetic field outside, so that the force, okay, will certainly be on the left hand side. And in order to calculate the magnitude, okay, we start with Ampere's law. So Ampere's law. So Ampere's law on the on the current I. Okay, I can say that B times 2 pi d, if I want to create an Ampere's loop of 2 pi d, and equals to mu I. Okay, so that B is equals to mu 0 I over 2 pi d, and I use this magnetic field from I, and then put into this QVB. Okay, and then finally you can calculate the force. Okay. Right, so this is another example about solenoid. Okay, so they give the parameter of solenoid. They give us L, they give us R, they give us I, they give us B. Then use the relationship that you derive from the solenoid. Okay, so let me try to derive the relation from solenoid again. So from solenoid, Ampere's law can be written in this form. So just magnetic fields and times by the length of the solenoid, because we have only magnetic field inside, and then on this side it become mu Ni, because this is like n turns of solenoid, so 3 times this by I. Then we have the magnetic field of mu 0 Ni over L. Then with L given, with radius given, we might not be using the radius, I'm not sure. And with I and with B, and then we are here, and they want us to find the length of the wire that forming the solenoid. So the length of the wire, we are going to calculate the length of the wire from the circumference of one turn solenoid, and if it does n turn, it will give us the total length of L times, oh, sorry. Oh, what happens? Okay, sorry, my screen just became a bit nasty, okay? But what we try to do is we try to find the total length of the wire, okay? So from these magnetic field inside solenoid, from this relation that we calculate from Ampere's law, we know this variable, we know we are given the B, we are given the I, and we are not given the number of turns, and we are given the L. So our unknown variable is N, or the number of turns. Okay, so now we can crack for the number of turns from the given information. Okay, but we want to find the length of the wire that forming the solenoid. Okay, so for solenoid for one turn with radius r, you need to use the wire of 2 pi r. Okay, to have the one turn of solenoid. But then you do another turn, you do another 2 pi r, you do another turn, you do another 2 pi r, then you do it n turns. Okay, you do it n times by 2 pi r. Okay, and for the n, for the number of turns, okay, you can be written in terms of the variables that you are given from by the question. Okay, then finally you can calculate the length of the wire that you use that needed for making solenoid. Okay, and this is the last example about toroid. Okay, about toroid, they want us to find the magnetic field inside the toroid at inner radius and the outer radius. Okay, so again we use the Ampere's law. So Ampere's law of the solenoid gives us mu 0 Ni over L. But for the case of toroid, I just replace L by the circle 2 pi a for inner radius, and I replace L by the circle 2 pi b for the outer radius, and then we can calculate magnetic field for both cases. Okay. So in summary, magnetic force, what we have from learning about magnetic force. We have that when charged particle is moving under magnetic field, they will experience force of QV cross B, and we learn how to use the right hand rule to determine the direction, and magnitude depends on the charge, on the speed, on the magnetic field, and also on the angle. Okay, depends on the angle. If theta is 0 or V is parallel with B, we have no magnetic force. Okay, and then for the case that magnetic field is uniform and V and B are perpendicular or making 90 degree, we will have a circular motion, and we can derive for the radius of the circular motion. And then for the case of current in the wire, okay, the form of equation changed from QVB to ILB. Okay, and also with the same idea, we can derive for the force that is acting on the wire. Again, and again, if the current is and the wire, if the current and magnetic field making 90 degree, we have ILB, which is the maximum force. But if the current and the B parallel, we have F equal to 0 or no force. And for the magnetic field sources, for the part 2, we learn how to use Ampere's law to find magnetic field in the case of straight line. Okay. we have straight line, and we learn how to find the magnetic field in the case of solenoid. Okay, so for Ampere's law, we try to create Ampere loop. Okay, and the Ampere loop making our life easy when the magnetic field is constant. So when magnetic field is constant, the integration become B times by the length 2 pi r in case of circular loop or circular magnetic field. So that we have this relation to find the magnetic field, and we try to apply this this magnetic field in some other case, such as we try to look at the case of two parallel lines, and here if I try to calculate the force F1 acting by the magnetic field from F2. So here I say that I2, okay, I2 will generate the magnetic field B2, and then I1 is sitting on B2, okay, is sitting on the B2. So that F1 will have the force from magnetic field B2 by I1 LB2, and then I use B2 that is calculated from Ampere's law to construct another relation. Okay, and then for the case of solenoid, for the solenoid, what to be noted for solenoid or toroid is magnetic field within solenoid and toroid is very strong. It is very strong because with many number of turns, okay, with many number of turns, there will be these many times of current within the Amperian loop. So if I construct the Amperian loop, that loop over n turns, okay, the enclosed current would be Ni. And then the integration of Ampere's law will be only B times by the length L, because we have only magnetic field within the coil, okay. And finally, the magnetic field within solenoid or toroid can be found by this relation. Okay, so it's pretty long lecture today, so hopefully you enjoy it, and don't forget to work on the work example. So we see you again on the example class and the tutorial class. Thank you.